What is a parity bit? Allow me to explain. To comprehend the term parity bit, you must first comprehend the terms bit and byte. A bit indicates whether a computer circuit is receiving electricity or not. A byte is comprised of 8 bits. What that means is that if you have a computer circuit, if it's receiving electricity, it will be marked with the number 1. If there is no electricity inside the circuit, it will be marked with a 0. Okay? 1 is a bit, 0 is a bit. Now, because all you're indicating with a bit is whether a computer circuit is receiving electricity or not, it will only be 1 or 0. See what I mean? Okay. So, if a 1 or a 0 is what is called a bit, then what is a parity bit? Well, we're going to get into that in just a second. Okay. Now, a parity bit is added to a byte. Now, as I said, a byte is comprised of 8 bits. 1, 2, 3, 4, 5, 6, 7, 8. So what they're going to do is they're going to add a 9th bit. Right there. So that's going to be bit number 9. And this is very crucial, and I'll show you why in just a second. Every day, data is transmitted from one computer to another across the internet. Parity bits help computers determine whether the data they receive is correct or corrupted. Okay? You have to have some kind of a way for a receiving computer. You have 2 computers. One that's sending information, another that's receiving information. That's how this works. Okay? What you have to do is you have to tell the receiving computer, you have to give it instructions on how to tell whether something it receives is correct or corrupted. Okay? And what happens is that there are these things called data packets. Now, I've covered this in previous videos. If you don't believe me, you can go through all of my other previous videos, and you will definitely find a video where I talked about data packets. Okay? And these data packets are sent electronically from one computer to another. Now, usually these data packets are just single bytes. Okay? So 1 byte usually is 1 packet. So if you have 100 packets, you have 100 bytes being sent from one computer to the next. Alright? Now then, when the computer receives the packets and opens it up and sees that there's a byte inside, it has to determine whether that byte is correctly received or if the byte was corrupted as it was transmitted from the sending computer to the receiving computer. You say, well, how does it get corrupted? Well, the sending computer may not be sending the messages out correctly. Or, as it's traveling along the data line, remember there are these data repeaters. Okay, and I talked about this in a previous video too. And every 1,000 feet, a data receiver will receive data, and then it will retransmit it so it can go another 1,000 feet. But you also have to keep in mind that when the data gets to a certain point, it's going to be set up through a satellite dish. And that's going to go to a satellite way up in space. And it's going to come back down to another satellite dish. And then it's going to go through a whole bunch of other data repeaters before it ever gets to your house. So there's plenty of ways that this message could be corrupted. Remember, this is nothing but electricity here that we're talking about. So it's just like a telegraph machine. Remember how they had the dots and dashes? Well, same concept. It really is. Okay? Now, let's take a look at this parity bit example we're going to set up right here. Okay. Now let's say we want to transmit from one computer to the next the lowercase letter A. How are we going to do that? Well, I'm going to show you how that is done. There is this thing called the American Standard Code for Information Interchange. Okay? And they have a whole list of characters. And some of them are letters, some of them are numbers. You have your $sign, your commas, your exclamation marks, your question marks, and all this other stuff. And each one of these things is represented numerically. Okay? So, if you're trying to send the letter A, you have to tell the receiving computer that you have sent the 97th character on the list of the American Standard Code for Information Interchange, or otherwise known as ASCII. That there is an acronym for the American Standard Code for Information Interchange. Going good so far, isn't it? Okay. Now then, how are you going to represent the letter A as bits? Okay, I'm going to show you exactly how to do this. Now then, we're going to first erase this here. Now, we know that the letter A is represented by the number 97. Now, each one of these bits represents something. It represents a number. 1, 2, 4, 8, 16, 32, 64. And I wrote this down wrong. That's okay. We just have to move everything over by 1. Not a problem. Stand by, people. I know I'm going to erase a bunch of stuff here. Just hang on. I forgot about our parity bit. So let's draw this over like this. Okay. 64, 32, 16, 8, 4, 2, 1. And this is going to be our parity bit. At the end, you have a parity bit. And I'll explain that in a second. Okay. So, is the number 97 greater than 128? No, it's not. Is the number 97 greater than 64? Yes, it is. Well, 97 minus 64 is what? Well, the answer is 33. So, what we're going to do here is we're going to say, since 97 here was not greater than 128, this gets a 0. Okay? But since 97 was not, since 97 is greater than 64, we're going to put a 1 right here. Okay. Now the next question is the number 33 greater than 32? The answer is yes. So I'm going to put a 1 right here. Alright. 33 minus 32, of course, is 1. Is 1 greater than 16? No, it's not. Is 1 greater than 8? No, it's not. Is 1 greater than 4? No, it's not. Is 1 greater than 2? No, it's not. Is 1 greater than 1? No, but it's equal to 1, so we can actually put a 1 right here. See what I mean? Now then, this row of bits is a byte now. Yay! You all seeing this? Okay, I'm going to move this over just a pinch so you can go ahead and see the parity bit. Now, here's the thing. We're going to add up these bits. 1, 2, 3. We have 3 bits that are on. That means that these 3 bits have electricity. The other bits don't have any electricity, but these 3 bits do. So basically what your receiving computer is receiving is an electrical pulse for this one, electrical pulse for this one, electrical pulse for that one. Okay. Now we're going to tell the computer that if the total of all three of these bits here is an odd number, then the transmission went through correctly. Well, 1 plus 1 plus 1, of course, is 3. So we can put a 0 right here, because if we add that 0 to all these, it's not going to change the fact that 1 plus 1 plus 1 is 3, and that it's an odd number. We now know that this number is odd. Okay? Now let's suppose we wanted to represent the lowercase letter b instead of the lowercase letter a. Let's do this. We'll do this. And I am sorry for moving everything around. Just bear with me. Now the lowercase letter b, like this, is character number 98. If you go to the chart of the American Standard Code for Information Interchange, let me make sure you're still able to read this. Good, that's very good. If you were able to read the chart, and go ahead and look up the chart. Go ahead right now, look up the chart of the American Standard Code for Information Interchange, and you look for character number 98, you're going to see that it's the letter B, the lowercase letter b. Okay. How are we going to represent that in bits? Once again, is 98 greater than 128? The answer is no, so we're going to put a 0 right there. Is 98 greater than 64? Of course it is, so we're going to put a 1 right there. Oops. Hold on. Okay. Now, is 32 greater than 32? No, but it is equal to 32, so we can put a 1 right there. Now then, 32 minus 32 is, of course, 0. So far, so good. So, 0 is not greater than 16, 0 is not greater than 8, 0 is not greater than 4, 0 is not greater than 2, and 0 is not greater than 1. Let's add up the bits. We have 2 bits. Okay? But we've told our computer that unless it receives an odd number of bits, that the message it's receiving is corrupted. Well, we've sent it 2 bits, so it's going to say right now that the message has been corrupted. So how can we fix that? Well, we're going to have this parity bit. I'm going to put a 1 right here. This is the parity bit, and I'm going to put a P right there so that you know that's the parity bit. So what's 1 plus 1 plus 1? Well, that's 3. Is 3 an odd number? You betcha. So when the receiving computer receives this, it's going to say, well, that transmission is correct because it has an odd number of bits. Are you seeing where we're going with this? Okay. Now then, you say, well, there wouldn't be a real problem with this, except for one thing. Let's suppose that we wanted to represent, let's see, let's go with the letter, let's say we're trying to represent the letter B, but it comes into our computer as the letter D. Okay? Now then, no, I got a better one for you. okay, let's do this. Let's say we decide that we're gonna send the letter B, which is 98, but it's gonna come to our computer as letter D, which is 100. Okay. Well, 100 is not greater than 128, but it is greater than 64. Okay? Now, 10 minus 4 is 6. And, let's see. 6 plus 4 is 10. And 1 and 6. 36. 10. So, now what's going to happen is that 100 minus 64 is 36. Okay, well, is 36 greater than 32? Well, of course it is. All right, that's going to be 4 right there. Now, 100 minus 64 is 36. So we've got to put a 1 in the 64 slot. 36, of course, is greater than 32, so we put a 1 in the 32 slot. Is 4 greater than 16? No, it's not. Is 4 greater than 8? No. Is 4 equal to 4? Yes, it is. Now, as you denoted earlier, what we're trying to send is 98. What we actually end up sending is 100. Now, according to this, the parity bit says that there's a total of 3, 1, 2, and 3 bits. 3 is odd, so the computer thinks that this is still okay even though we were trying to send B instead of D. You see a problem with that? You say, well, half the time now we're going to get the data correct because it's going to look for an odd set of bits, and if they're not odd, we have to switch the parity bit so that it will be an odd set of bits, so it'll read it correctly. But the thing is that, what if you're sending the wrong letter? Or what if the receiving computer thinks that it's this letter, but this is one you actually sent? Somehow it got corrupted in the transmission, and now it says that you're supposed to receive a D instead of a B. Well, the parity is going to be correct, because after all, 3 bits, it's odd. This whole total is odd, so therefore the computer is convinced that it got it right, even though it didn't. You say, well, how do you prevent something like that? Well, in 2018, I'm going to present a video on the checksum. I'm going to explain checksum to you, and when I do, I'm going to show you how we can keep those kind of errors from happening when you transmit data from one computer to the next. Okay? So even though the parity bit is all okay, you're still getting the wrong data. How do you prevent that? Well, I'm going to show you. But I will show you that in 2018, so I hope you will hang in there, and I hope you will stay tuned.